All right, class, the first thing I think we got to do is vote on when we're going to have our examination, or when the first exam is. So I asked you to consider it and give me some dates. Now, I'm going to suggest, you can give 2 or 3 dates, we'll vote, and if it's close between 2, we'll vote on the last 2. So do you have any dates you want? Give me both the day of the week and the actual date. Anybody? Pardon?
October 10th.
October 10th.
That'll be Wednesday.
Wednesday before.
All right, this is Wednesday. This is October 10th. Keep going.
Monday, October 8th.
Monday, October 8th.
And Friday the
Friday?
12th. It's a Monday.
Friday, October 12th.
No,
That's
we're
fall
not.
break.
No, we don't have plans.
Oh, I'm sorry. Yeah.
Well, let's not do that day. What do you want the Friday before?
Friday is Saturday.
October, what?
Oh.
You can do it Saturday.
You can do it Saturday, I can't. I mean, is there any other dates? It makes sense about that time. You can do it sooner if you want, doesn't matter to me. It's always going to be, the material is always up, the material up to the day, the class before the test. So it's always comprehensive, it's always closed book, it's always closed notes. Remember that. And so anyway, that said, now the dates,
So we need to stop.
I'm going to make one comment. I mean, if you want another date, I'll put it, but
Okay, October 3rd, Wednesday. No, that's one. Man, he just said
October 3rd. All right, now that's fine, but I'm going to make one comment. I do this every time, I let you vote on it, I don't care. In general, over the years of experience, with very few exceptions, the highest grades on average are on a Monday exam because you have the weekend to study. I'm just saying that some people don't study on the weekends, obviously theirs don't reflect it. But the majority of the class is serious about their exams, and the more time they have, like over a weekend, usually the higher the grades. And I have seen this, I have seen it all over the place, even in graduate courses. It's always the Monday exams are highest. Fridays are the worst usually, because you're burnt out from the week. Just being honest with you. Wednesday's somewhere in the middle. I don't care when it is, you vote. I'm not saying that's going to be the rule of thumb for everybody, but that's what I found to be true. So if you want it, we'll take the top 2 and have a runoff, but now you get one vote and only one vote. You count with me, all right? And you count with me. Make sure I don't make a mistake. So you get one and only one vote and one arm up. If you want it, Wednesday, October 3rd, one arm. Wow, that's easy. You didn't even vote for it. If you want it Friday, October 5th, one hand. All right, hold them up there. I'm counting 2. Is that right? 3. 3. I got 3.
Yes, go.
All right. Monday, October 8th. One and only one. Oh my goodness. I got. Hold them up. Hold them up. All right. 2, 4, 6, 8, 10, 12, 14, 16, 17. That's it. I mean, you can play the game. If you want a Wednesday, October 10th, one hand. One. We don't need to revote. All right. It's Monday, October 8th. Here's the tip. A tip right now. Start studying daily. I mean, not only do the homework, start reviewing, especially convolution. All right? I'm giving you a tip, dude. If you spend just 30 minutes to 45 minutes on a review, besides doing it, you'll find yourself, you'll have a tremendous advantage. No matter what your friends think, just do it because you want to make a good grade. It's not their grade. It's your grade. Your friends will do one thing to you. I found out all the good time people. They will take your grade and flush it down the toilet. They will destroy you faster than you can think, but any could. Because you trust them. All right, now, getting back to the today. I have some things I want to cover. I know I'm going to take questions. Are we fixed on this exam? Monday it is, all right? And I always say this to people, but they don't listen. Now that's a late afternoon, a late example. You have a course, you have classes earlier. Get your sleep. You don't know how much sleep does. You want to really ruin your day? Get 3 hours of sleep and try to take a comprehensive examination. There's a lot of thought involved. You'll flunk faster than anybody imagine. And I don't mean you can do that with history. I know people can cram and do it. Where it's just memorization. Engineering ain't memorization. It's like playing chess. You gotta be on your game and be able to be logical, deductive, and creative at the same time. And you have to remember a lot too. Now, here's what I want to cover before I start getting questions. And there is a quiz. The thing I'm going to cover is the Fourier transform properties. These are the things I see as critical. I'm going to go through some specific transforms that are critical in my mind. Now, I've told you a lot of the stuff with Laplace is applicable to any function that is 0 before t equals 0. You can just take the Laplace transform and change s into j omega, and voila. So that saves an enormous amount of time, but there's some you can't. And that's the ones I focus on. And I'm trying to teach you as I would want to be taught if I was in your shoes. It's applications, how to do things right as an engineer. So the first thing I want to do, one property I didn't cover was, this is the really scaling. If you have x of t, always assume it goes to some x of omega. I always start there. We're assuming we know this. We know some function in its actual transform. Now, this is actually a property that you had with Laplace transform. Suppose I have x times at. Happens all the time. Now I have a coefficient in there. Instead of just p, I have an argument at. Over here, you remember that, without proving it, do you all remember that's just going to be 1 over a x of, and it would be s over a here, but now it would be omega over a. You all remember that one, class? That was scaling. Remember that one. You'll use that a lot. Next, I'm going to do something. I can show you an example of this, but this is relatively trivial. Next thing I'm going to do is a function that's real important that you know the transform on. This is the pulse function, p tau of t. The book calls it rect, R-E-C-T, of t over tau. Do y'all remember me talking about this, class? The rect function or the pulse function? Well, for this one, I'm going to draw it up first to make sure everybody's got a picture of it. Any of these functions, it's always smart. If you're not real sure, draw them. Make sure you know what we're talking about. So for this function right here, what it looks like, and I'm going to do it here, it looks like this. If this is t, the pulse function of t just has a height of 1, and it goes from minus tau over 2 to tau over 2. Now, I'm going to say this about that function. It's symmetric, it's an even function, has a height of 1, it's just the width of tau. This one has it's centered at t equals 0. Now, the Fourier transform of this is very important. You'll notice that it has values for t less than 0. Do you all see that? Therefore, it does not have a definitive Laplace transform. Remember that. This is one of the unique ones that doesn't have a Laplace. So when we take a look at this and we get the Fourier, we're going to get the Fourier transform of that. This is going to be equal to, remember, the fundamental Fourier transform of this is x of t. Just say this is equal to x of t. Well, x of omega here would be equal to the integral. Technically, it goes from minus infinity to infinity of x of t. I'm going to put the pulse function in here, and I'm going to change things. Times e to the minus j omega t dt. That's the definition of the actual Fourier transform, right? And I simply put the pulse in. But we know that pulse is a value of 1 only between minus tau and tau, right? And it's 0 otherwise, right? So how can we modify this? So it's easily doable. Guys, how about the limits? The limits would go from minus tau over 2 to tau over 2, agree? Anywhere else it's 0. So it goes from minus tau over 2 to tau over 2. And what about p tau of t? What do we replace it by?
1.
Just 1, right? Because that's its value. So we get rid of it. And we do the integration. Now when we do this integration, we find we get 1 over minus j omega times e to the minus j omega t, evaluated from minus tau over 2 to tau over 2. Right? I told you something, that minus sign could be up top, couldn't it, class? What do I do with minus signs? Yeah, what do I change here? Limits, right. I make this plus, this minus, right? And get rid of that. I'm going to leave the j downstairs now, all right? Now, when I do that, I see this is really what? This is 1 over j omega, right? Then it's going to be e to the minus j, instead of t, it's minus tau over 2. So it's e to the j omega tau over 2, right? Then it's minus e to the minus j omega tau over 2. Does everybody agree with me here? I'm not quite done yet. You all agree? Now, by this time, you've probably been keyed in on the fact that that sure is starting to look like it'd be replaced by a sign. Do we agree? But I also told you about the sinc function. And now we're going to use sinc over and over. This is where we're going to use it. So for the sinc function right here, we know the sinc of x is defined as sine of x over x, right? That's the definition of rsync. If you are in other classes, they'll have a sine of pi x over pi x. And the only reason they do that is so the 0 will always be an integer values. Don't worry about this. This is the one we use. This is our definition. So when we take a look at that, first, I can say that, does everybody see how this can be replaced by 2j sine of omega tau over 2? Do you all see that right there? Give me a show of hands if you do. This entire thing right there that I'm circling can be replaced by sine of, or really 2j times sine of omega tau over 2. So I'm going to come down and I'm going to say this. I'll just go over here. This is going to be 2 times j sine of omega tau over 2 divided by j omega, right? Work with me now. You all agree with that? I'm not trying to go fast. I'm trying to make sure you see it. Do you all see it? Over here? All right? Now, you see the j's cancel? Does everybody see that? I got j on top, on the bottom, so that goes away. I'm going to do this one last time. Some of you probably are looking, I'm not quite there. The sine of x is equal to e to the jx minus e to the minus jx over 2j. And therefore, 2j sine x is e to the jx minus e to the minus jx, where x is now omega tau over 2. Yes?
If that was e to the jx plus e to
That's
the...
cosine now. All right, don't worry about that. That's cosine. If you want me to, I can put it here. We're not going to use it right away. If we have cosine of x, it's e to the jx plus e to the minus jx over 2. That's, all right, I'm just putting it there for you. So now, I want to make this look like that. Can I divide top and bottom by 2 for starters? I only need omega tau over 2. Do you agree? I divide the top by 2, I get 1, bottom by 2, I get 1/2. Now what do we need? Remember, I'm looking for this to be this. Multiply by tau, top and bottom, right? Do you agree with me? I'll stop for a second. You all see what I've done? You know why I'm doing that? I need this argument, which is what? Omega tau over 2 in the sign to appear down here, right? Now, do you all see that I have the sinc of omega tau over 2? Everybody? Right? Isn't this sine of omega tau over 2 over omega tau over 2 that, where x is now omega tau over 2? And therefore it's sinc of omega tau over 2? It sure is. So now this is really tau times the sinc of omega tau over 2. Got it? You all see it? This is very, very important. This one you got to know. So the transform of that is tau times the sinc of omega tau over 2. And that's very important. All right? Is everybody with me now? I'm going to sketch this just for a second so you all see this. What I'm going to sketch is this right here. This will really help, I think. The sinc function is an even function. And what sinc looks like right here is this. If I'm just going to do the sinc of x, it starts at 1, and it does this. At pi is the first 0, 2 pi, 3 pi, and it's going to asymptotically decay in magnitude, like that, where this is just going to decay as 1 over x. It's proportional to 1 over x. Y'all see that? Now, typically what they show is the magnitude of the sinc function. So if you took the magnitude of the sinc function, here you get this. Oops. Where this, you can see, is asymptotically decaying. This height would be 1, this would be pi, 2 pi, 3 pi, minus pi, minus 2 pi, and so forth. You all see this, class? So if you got a pulse waveform, you get a sinc waveform. You'll notice the width from here to here is 2 pi. From the first null on this side to the first null here, it's 2 pi. You all see that? That'll become important later. I'm not going to go off on a tangent on this thing, but that sinc function will be very important. And you can literally say that omega tau over 2 would be equal to 2 pi would be the width. And I'll stop there. I'm not going to get into that yet. You all see what I'm talking about here? Just realize that's the general shape. Now, the next thing, that function is real important. I'm going to go through some of the properties that become essential, you know. And I'm going to put them all down. I'm going to conflate properties as well as transforms. This is really a transform pair, but it becomes so important that I'm putting it right here. This is stuff you need to know. It's not a problem. What time is our game anyway?
2:30, I think.
Is it 2:30? Okay. They're at 11:15. All right, now I've already done these before. I'm just going to populate this actual table I'm making with information. These are properties, but we've done these. If I have e to the j omega naught t times x of t, knowing this relationship, this is simply x of omega minus omega naught. So whatever the transform here is, you just shift it by an omega naught. If I have x of, this is an e here, if I have x of t minus alpha, what comes over here? We did this last time. Just think Laplace. Guys, girls, what?
E to the negative alpha t.
Right. It would be e to the what?
Negative.
Minus j omega alpha, right? Times what? Times x of omega, correct? Instead of s, you just put in j omega. That's the whole game here. Right? After that, I'm going to come over here and keep going down. I'm going to do this way. Remember what 1 was? I did that with something called reciprocity that I really, really underscored the importance of knowing reciprocity. Do y'all remember that? What about 1? That's DC, isn't it? It can be rendered this way. 1 can be thought of as simply u of minus t plus u of t. You're going to have a problem right at the origin, but that's where we kind of ignore that point. But u of t plus u of minus t is always on, isn't it? It's always 1. Just at the origin, there's that part about 2, so that they have a special way of dealing with this. This is a good approximation. When it's 1, do you remember what it goes to? Let me ask you this logically. If you just have DC, 5 volts, it's on since the beginning of time, is there any frequency variation?
No.
No. Where do you expect all the information of frequency domain to be? At omega equals? 0. Where do you think it is?
A delta function.
A delta function of omega, right? It only turns on when omega is 0, right? It's got an infinite amplitude. But it's weighted by 2 pi, right? 1 becomes 2 pi delta of omega. Do you remember me doing this with duality? Do y'all remember that? I mean, so critical you remember this stuff. When I come over something, I expect the next class you've got it. All right, because if you don't, you're going to get killed. I mean, you've got to stay sharp in this class. You can get absolutely destroyed. Again, with duality, it says if you have x of t, and you know the relationship to capital X of omega, this is duality. Then if I take this functional form over here, whatever the functional form is, and I replace omega with t, right? Then over here, I take the small argument, x of small t, and I simply, so I'm trying to make this look. I take this as 2 pi times x of minus omega. Do you remember me doing this, class? Remember, and what did I do? I went delta t here, went to what? 1 here, right? Therefore, 1 over here goes to 2 pi. Instead of delta t, it's delta of minus omega, right? But I know delta of minus omega is delta of omega. That's where I got that. Agreed, class? Come on, stay sharp with me. Now, so let me just do it this way. 1 goes to this. Now, I also did something with a property. I said if I had x of t times cosine of omega naught t, do you remember what it rendered? People? First thing is 1/2, right? Remember, 1/2. It's going to split that transform. It's going to be 1/2 times what? X of omega plus omega naught plus x of omega minus omega naught, right? That's modulation, critical, AM modulation, right, class? Now, knowing that, just listen to me. We're going to keep working here. What happens if I want to transform, some of you probably know this, of just cosine of omega naught t? You'll notice that's been on forever. It doesn't start at 0. It's been on forever. How would you do that based on the prior two things I said? Doesn't cosine of omega t look like 1 times cosine of omega t? Do you agree with me? 1 can be thought of an x of t, as an x of t. It doesn't vary, but it is, in fact, something that can be thought of. You'll notice when x of t is 1, it goes to 2 pi delta of omega. Do you see that? Therefore, my x of t here would be 1, and it would go to 2 pi delta of omega, right? Therefore, if I multiply by cosine, now I have to do this, right? So now I say this will go to 2 pi over 2 times delta of omega plus omega naught plus delta of omega minus omega naught. Which means this cosine omega t, do you all agree the cosine omega t only is at one frequency? It's at omega naught, right? Therefore, if you peeked into the frequency domain, you expect everything to be at that frequency. Do you agree with me there? If it's only oscillating at omega naught, we surely shouldn't get something at omega times, or 5 omega naught, right? It should only be at omega naught. Do you agree? And look, in fact, what happens. You've got a strong delta function at minus omega naught, and a strong delta function at plus omega naught, and nothing in between. Do you all see that, class? And the way I got it was using this property, where my x of t is 1, and I know 1 went to that, and therefore when I put 1/2 times 2 pi, I get 2 pi over 2, or simply pi, right? I can just make that pi. And lo and behold, that's it. And it's an easy thing to understand and do. Nothing hard about that. Now, let's see here. Oh, yeah. Now, I want to tell you one other thing about Fourier transforms. Sometimes a Laplace transform, I said this, maybe I should have actually cautioned you. When I said that any function that is 0 for t less than 0, and all the values that are non-zero for t greater than 0, allow us to simply take the Laplace transform and take s and allow it to become j omega, I omitted one fact, and that is that the integral of any function that you want the Fourier transform for, from 0 to infinity, has to be finite. If it's not finite, it means it's a special type of function, and then you have to do something tricky. You can't just replace s with j omega. What I'm trying to say is now the U of t function becomes a little problem, it becomes a problem. So I'm going to try to explain something to you. First, I'm going to show you why U of t is a problem, and then I'm going to show you how we solve the problem without getting into some really crazy stuff. So if we just wanted the function U of t and we wanted the Fourier transform for it, we could go to the fundamental definition and we could say this transform here would be equal to the integral from minus infinity to infinity of U of t times e to the minus j omega t dt. You all agree with that? Now, help me out here. How do I evaluate that? Lower limit would start at? Upper limit would go to infinity. What do we do with the U of t? Make it 1, right? Because from here to here, it's always 1. Now I do that integral, right? Follow me on this. This works with a plus. It doesn't work here. When I do that, I get 1 over minus j omega times e to the minus j omega t evaluated from 0 to infinity. You'll notice that minus sign I can bring upstairs, right? And what do I do when I get a minus sign? Just change the limits. Make that 0. Make this infinity, right? Sorry?
I was just gonna say, if we move the J up to the top of it.
No, I want the J done.
That's
I like it where it is. You're right, we could eliminate it. I'm just leaving it like that. Now think about that for a second. That's equal to what? That's 1 over j omega, right? And then I got e to the 0, which is 1, minus e to the what? Minus j omega times infinity. Anything troubling about that? That's oscillating up and down, up and down. Pick a value, any value at all for infinity, make it 10,000, right? Add a little bit more to it, 10,000 plus what? Pi over 10? It changes its value. It keeps changing. It's not asymptotically approaching a singular value. And this is one of those things that's undefined mathematically. We have to look for an alternative way to get this transform, but it is doable, and I'm going to show you the trick. I'm going to go through it, kind of show you how mathematicians deal with oddities like this. Now I'm going to tell you this much too. You know how I get 1 here? If I put 1 in here and do that integral, it would be the same problem. We'd have e to the minus j plus and minus infinity if we try to evaluate it direct, like this. But you'll notice I used what? Duality to get that, didn't I? Right. I got that transfer. This one I'm not going to use duality. I'm going to use a different trick. I'm going to do it here too. I'm going to create a function that's very useful. It's called the Sigma function. How many have heard of the Sigma function? Y'all heard it? Mathematicians, look this. I'm going to erase this right here so I can use this important. You'll see why it's important. This is it, and the real reason it's so important, it allows us to do things in the time domain to get the actual Fourier transforms for functions that aren't generally doable, easily doable. So this is what sigma t is. It's really SGN of t, and it looks like this. If I plot, if this is t, it looks like -1 all the way to 0, and then it goes to +1 here. So it's either -1 or +1. And a lot of times they render sigma t as u of t minus u of minus t, but then they do something else. They weigh this by e to the minus epsilon t, and they weigh this by e to the epsilon t. And what it does is this, just put that down what I put there. Epsilon is going to be approaching 0. Here for this function, they're going to take the limit as epsilon approaches 0. But I need to show you something, why they're doing it. See, as epsilon approaches 0 right there, don't we just have u of t and minus u of minus t class? Do y'all see that? Are you with me? But watch this. Let's assume epsilon ain't 0. It's just trying to get there. Here's what this function would look like. It would look like this. And here, it would look like this. Basically, it would be asymptotically or exponentially decaying depending on the value of epsilon. Do you all see that? Now, what that means is this, that for this function, the area under this curve from 0 to infinity or from minus infinity to 0 is finite. It's not infinite. If we let epsilon have any value that is not actually 0, any finite positive value, are you with me? But this is the definition of this function, and here's why they do it. And you'll see this and appreciate it, I hope. Now, if I use this definition of sigma t, you give me that right now. It's a cockeyed one, but it'll serve the purposes. If I take this and I stick it in to the actual definition of the Fourier transform, I can say that x of omega here is equal to the integral from minus infinity to infinity of that function, which is going to be e to the minus, e to the plus epsilon t times u of t, for the minus sign, plus epsilon minus epsilon t u, that's minus t, pardon me, this is minus t here, and this is u of t. It's all that times e to the minus j omega t dt.
Now, is that actually epsilon to the negative epsilon t, or you mean e to the negative epsilon t? In the second?
On the left.
Oh, this is e. I'm sorry.
Yeah, you did the
I
same
do
thing
that.
over here too.
I write them, honestly, when I write epsilon, I do it. I'm sorry about that. And a lot of the work I deal with, they use epsilon symbol like that for e to the power. I'm just telling you, sorry about that. Are you with me, class? It's an exponential in both cases. Now, what I'm going to do here is, since this is on for t from minus infinity to 0, I just take the limits and go from minus infinity to 0 with this part of it. For this part, it's only on for t greater than 0, so I break it up into two parts, and I say x of omega is equal to the integral from minus infinity to 0 of minus e to the epsilon t, right, times e to the minus j omega naught, or j omega t dt. And then I say it's that, there's a minus there, plus the integral from 0 to infinity here of e to the minus epsilon t times e to the minus j omega t dt. Now, you can see I can combine these exponentials here and here easily. And once I combine those exponentials, I can do the integration. I can get minus e to the what? It would be epsilon minus j omega times the quantity t, right? So when I do this integral, here's what it becomes. It's going to be minus 1 over, and it'll be epsilon right here, minus j omega here, times e to the, and then it would be quantity epsilon minus j omega t, j omega, pardon me, times t, evaluated from minus infinity to 0, plus, and then it's going to be, for this one, uh, 1 over minus epsilon plus j omega times e to the minus epsilon plus j omega times t, evaluated from 0 to infinity. I'm just breaking it down doing the integration. Remember, I collected the coefficient of t. It's epsilon minus j omega there, and the coefficient of t here is minus quantity epsilon plus j omega. Then I did the integration. Now listen to me here. Remember, we're going to allow epsilon to go to 0. Do you all follow me? Take a look here for a second. When I do this one, and I do this one's negative, so I'm going to change the actual, I'm going to minus sign, I'm going to change the actual limits here. So this one will go from infinity to 0. I can see why. Now just look at that for a second and follow me on this one. When I do this, after all is said and done, I end up getting is going to be minus 1 over epsilon minus j omega. And this is going to be times quantity 1 minus e to the minus, or excuse me, e to the, minus epsilon minus j omega times infinity here. And then it's going to be, I'm going to run out of room here, I'm going to have to take that plus 1 over epsilon plus j omega times the quantity 1 minus e to the minus, and it would be epsilon minus j omega times infinity. Just work with me here. I've just completed it. And I want you to notice one thing that's critical. That's a minus sign. That's a plus sign. Minus times minus is plus. Plus times minus is minus. With me? You'll notice that this last term right here and this term right here cancel each other out. Exactly. Are you with me? Then as you allow epsilon to go to 0, I'm running out of time here. As you allow epsilon to go to 0, the transform actually becomes 2 over j omega. I didn't get through everything I wanted today, but so that means if we come down here, I'm just going to put it here. If we have sigma of t, it will render 2 over j omega. That will be the transform. You're going to have to, it's in the book on some page, and I don't know where it is, but it's in the book and it's discussed. It's part of the reading. How many remember seeing this in the book? Did anybody read it? You did? Did you read it, Josh?
I've been booked this week.
All right, well, it was in the book, and it's very well discussed. I'm trying to elaborate on it. That's the actual execution of the integration. Go ahead. You had a question?
I was just wondering if you could work on the homework problems.
You guys are really going to get me one. You're going to get me to put the quiz on Monday.
It's not that, it's just I really am kind of lost with this.
All right, you'll get it Monday.
We love you.
No, you don't. Don't lie like that.
No, we ain't.
When you start throwing stones at me, then I'll feel you get honest. I hope I didn't say anything that's going to give me too much trouble. All right, let me erase this stuff and I'll work the problem. Is there any big game this week in the SEC, by the way?
I don't know about the SEC.
How about a big game in general? Anybody?
Ohio State's playing Penn State.
Penn State. I don't know if that's going to happen. Ohio State's pretty tough. Where are they playing?
I think they're at Ohio State, but I'm not
Oh,
sure.
bad. If they win that game, I'd be
I
surprised.
could be wrong about that.
Ohio State, Penn State. All right.
I think that's where game day is this weekend.
That was a big game when I was You know, down here, what's the big game of the year? The Iron Bowl, right? I mean, honestly, in the SEC, maybe there's a bigger game, but I don't know about it. Up there in the Big Ten, it's Michigan, Ohio State. It's world war up there. I mean, they hate each other. Down here, they hate each other, but over there, there's a lot more people that hate each other.
You guys Bills versus the Packers? this
What's that?
Sunday? Bills versus the Packers this Sunday?
Well, I'm not an NFL guy anymore. I'll watch Brady once in a while. Occasionally, I watch Cam too. But, I'm not there. I'm just not there anymore. All right, which one did you have for me?
I'll do one of the simpler ones like 5.40. It's,
Oh, goodness, the drawn, and now you're talking about how do I define the function mathematically, right? Where do you want to start? Which one? Doesn't matter.
it's basically a triangle function spanning from negative tau over 2 to tau
All right,
over 2.
I didn't get this down, write this down, write this down. This is a function, first I showed you what, that p tau of t went to, I didn't have time to prove this, went to what, tau, I proved this one, tau times the sink of omega tau over 2. Do y'all recall that one? We did that. If there's one thing you gotta know that one.
Is that sync or sine?
Sink. Sinc, S-I-N-C, of omega tau over 2. Thank you so much. Right? You know that. Here's one I didn't do. It's the triangle function. I defined it before. Normally, what we do is show a triangle function like this. Mathematically, the triangle function is this. It's 1 minus 2 magnitude of t over tau times the pulse function p tau of t. That's the definition of the triangle function. You can work that out on your own. But what the triangle function looks like is this. This is the triangle function. All right? It's like a pulse function, only it's tapered. Now that function, I'm not going to have time to do the actual transform, but just write this down. It's doable. This function transforms to not tau, but tau over 2. And then it's the sinc squared, not sinc, but sinc squared of omega tau over 4. These two commit to memory. Work with them. They'll save you. All right, that's so important. So now I got the pulse, and I also got the triangle function. I'll prove that next time if you remind me, all right, on Monday. It's a great function, remember that. But this is a direct transform. Now, all the things that I gave you can be mathematically defined. I'm going to start with the first, and then you'll see all the rest based on these. Work with me. First function I gave you to do was, correct me if I'm wrong, this was time, and did it go out? Did it just ramp up to 1 here? Where did it ramp to?
A equals 10. It ramps up.
What point is this right here? 3, and it went to A, and it's just a straight ramp, right? Agreed?
It goes to the other way. It meets at the y-axis, like the tip of the triangle's at the y-axis.
Wait,
No.
no,
That's right.
number 39, that's right. That's right.
This is the
I
first
think I'm looking at the
problem.
wrong one. my
Is
bad.
this supposed to be A there?
Yes.
Yes, it
What about
is.
this?
That's
Capital T.
Oh, T, good, good, good. Even better, it's generic. Now, look, this is a very typical thing. I would ask this, guaranteed ask this, but I'm not, this kind of a problem, what does it look like? It's a pulse, right? Or it's U of T's, either one. Why do we do it with U of T's? You guys asked me about this last time, right, didn't you? So this function, can I describe x of t here as simply, well, that looks like, we want a straight line equation for that. Doesn't it look like a slope of a over t times t? So we could say that x of t here could be defined as a over t, that's the slope, times t. That's a straight line, right, that goes on and on forever. But I don't want it forever. I want it to start at 0. How do I start the thing at 0? U of t. Now it's on. It's been off from minus infinity to 0. But I want it to stop at t. How do I stop it? Minus u of t. This is one of them. Minus, right? Minus u of t minus cap t. Now, isn't that only existing between 0 and cap t? And the weight t times a over cap t is the actual line that it's taking a cut out. You agree? Let's go get the transform of this one. I'm going to do it quickly. If you guys stay with me, I'll do a few more today. I mean, I'll show you how to whip these things in a heartbeat. They're easy. So if we take a look at this, there's two functional things we have to consider. We have U3 actually. U of t, we want the transform of that. Do we have it? Yes. U of t minus tau. That's what? That's like x of t minus tau. Do we have that transform? Yes. It's time shifted by e to the minus j omega naught cap t, right? Then there's a t waiting. Do we have t times x of t? Yes, right? We've done that. What is that? That's j times the derivative with respect to omega of x of omega, correct? Are you with me, guys? All right, I'm moving a little quick. If you've thought about that problem, you probably understand what I'm saying. How many understand this? I'm looking like Ed. Don't even talk to me about understanding. All right, just watch me on this one. Let's go here and just populate. Y'all give me u of t, we just did, goes to what? well, maybe we didn't just do it, but we were about to just, 1 over j omega plus what? Pi times delta of omega. You give me that one. No? Wait a minute. Yeah. Y'all give me that one, guys? Right? I'm getting these looks like, really? I never saw it. All right. Now, what happens if I have u of t minus cap t? What does that go to? What? Come on.
Delta omega.
No, do the time shift first. It's just what? E to the what?
Negative.
Minus j what?
Minus j
Omega cap t times what? 1 over j omega, right? Minus pi times delta of omega. I'm a little tired, so it's going to get goofy in a second. Y'all agree with that? Y'all see how, what do I got here? I got this junk out, don't I? Right? Well, I'm about to get that junk. I'm going to take this and subtract that from it in a second. Then I'm going to weigh it by a over t. That's scaling, isn't it? Right? So let me go ahead and do this. I'm going to come out here and do it. Let's do it over here. So now I'm going to say, if I have u of t minus u of t minus cap t times, just scaling it, a over t, then that goes to, now notice the a over tau, or a over t, comes out in front. That's scaling. The u of t goes to this, right? The u of t minus tau goes to that, right? Only there's a minus sign, correct, class? Now, if you look at that, do you realize you can factor out this part, 1 over j omega plus pi times delta of omega, take it out in front and just multiply by 1 minus that e to the minus j omega, please sure you can. So I can say this goes to simply 1 minus e to the minus j omega cap t times 1 over j omega plus pi times delta of omega. Did y'all give me that? Agree? And that's my x of t, correct? Now, do you agree with it? What's that? I'm not done yet. Yeah, I'm just saying that's x of t. I'm going to multiply, well, it's x1 of t. I'm going to multiply that by t in a second and use the property next, okay? Are you with me? So now, next I come here and I say if it's t x of t, or x1 of t, now what does it go to? J times of x1 of omega, correct, class? Look at the property. Do y'all see that? Isn't that it? All right, I'm about out of time, but y'all agree you can take a derivative of this with respect to omega? And you can put a j in front of it, can't you? Here's the one thing that's not in the book. Well, it's in the book, but I think it's in the book. It's not discussed well, and this is important. When you have a delta function, this is the thing. If you take a derivative of u of t with respect to t, you get, it's equal to delta of t. That is the definition of the delta function. Do you follow me on that? If you integrate a delta function with respect to t, you get u of t. Take a derivative of u of t, you get a delta function. You all know that, right? Now, if you take a derivative of a delta function, this is not explicit in the books, the early part, but it is there, I believe. If you take a derivative of delta t, now you get something called a doublet that you aren't really required to know. A doublet is this. It says that you're going to take, and it'll just have a sub 2 on it of t. And what a doublet is this. Since it's a derivative of delta function, if you think of a delta function, it goes from nothing to infinity and back to nothing again, right? Give the delta function a little width and think about that derivative. It looks like a delta function this way and a delta function this way. A doublet is basically this. It's 2 delta functions that are next to each other. Now, you don't even have to worry about this until you're, until your controls class, I think. But I just want you to be aware of that. The trick is with this, when you do the derivative of this with respect to omega, you're going to get derivative of this plus this times the derivative of this, right? And you're gonna get a doublet here that looks weird, just ignore it. Because it effectively means zero, it's zero. Understand that, class?
It gives you the derivative of pi, right?
Well, it's pi times the doublet, but don't worry about that part. Just worry about when you do this, put your hand on that thing and do it. All right, and that would be the right value, or the right function. Guys, I didn't mean to take that much time. You wanted me to do another one? I'll stick around. If you want to go, go, but I'll do it for you until I get thrown out of here. I mean, you're welcome to stay, but you don't have to. One, Megan?
I
What?
was talking it now. Didn't know if you wanted that one down. It was drawn like your first picture.
All right, hold on. Let me get it up. Whoever asked it, if you want to stick around, this is, consider this an office hour until I'm forcefully removed. Megan? All right, now we're off the record. You can leave it running, but remember, this is not class, this is fun. So go ahead. You can say what you want. Which one? Wait, is that one?
Yeah,
The
it
triangle?
was drawn like yours. It goes from
That's easy. That's the triangle. Let me just do it for you. Which problem is that?
40.
It's, what's it, 540?
Yes, sir.
And it looks like this, right?
Just
Height of A, this is what?
negative capital T over 2.
No, right
T
in
over
there.
2.
This is T over 2. This is the one I just did, isn't it?
Yep.
Yeah.
This is, let me define this. This is a triangle function. We'll define this. This is actually what? A times a triangle function, right? The width of it would be T of T. Well, this one, I didn't prove it, but this one will become A times tau over 2. The width of this is T, not tau. So it's A times T over 2 here times the sinc squared, and this would be omega cap T over 4. Not 2, but T, omega cap T over 4. Does the book have a triangle function that transform pairs for Fourier or not? They should have a pulse, a rect. Do they have a rect function? Rect, a T over tau?
A rect T over tau, yes.
And they don't have a triangle? Do they have something that says like, I showed you, they have 1 minus magnitude of T over, or 2 times magnitude of T over tau times a pulse, or the rect function?
Yeah.
They do?
It's tau sync omega.
Sinc squared?
It's just sync omega.
I don't worry about it. This is the right one. All right? Get that down. Now, so that's easy for 540. Which one did you want to ask me about?
Probably 542, but that, you can probably just segment it.
Now you take a block, right? You take a pulse plus a triangle. Let's do it for everybody's benefit. So I think the one you're asking about, which is a good one, you're saying x of t looks like this. What's the width? Where does it start at?
It
Minus?
starts at 0 to tau, and,
Oh, 0.
yeah,
That's a little different. Okay, it starts at
and
0.
segmented into.
Oh, hold on. Starts at 0
Yes.
and ends at,
Tau, and there are 2 subsets of tau over 3 and 2 tau over 3.
Wait, that's capital T. It's capital T. It goes all the way to capital T. And then so from 0 to capital T over 3, you
hold
stay
on.
at A.
T over 3. Oh, this is stair step thing?
Yes, sir. So
It's a third A over 3 here?
It's
No,
A
Have
over.
A over 2 and A as the y values.
All right, this is A over 2 here. It stays until this point. That goes to A.
No, it starts at A.
Starts at A, stays at A till, t over 3.
Hold on. It
Yeah.
starts at A. Go ahead.
Yes. And remains at A until t over 3, and then goes down to A over 2 from t over 3 to 2t over 3. So it's angled slope down.
Oh, it's slowly changing.
yes, it's
Yes.
slow.
It's going to go,
It's
wait a second.
basically-
Is this a slope here?
Yes, sir.
Okay, so, I mean,
To have it.
perfect. And
And
then,
then it remains at A over 2.
and then this?
And that's it.
Now, oh boy, I gotta get out of here. I got a class looking at me. I thought we were free to do this. All right, well, you want to do it in my office? Come on up.